In our previous lesson, we introduced you to stack data structure. We talked about stack as abstract data type or ADT. As we know, when we define a data structure as abstract data type, we define it as a mathematical or logical model. We define only the features or operations available with the data structure and do not bother about implementation. Now in this lesson, we will see how we can implement stack data structure. We will first discuss possible implementations of stack, and then we'll go ahead and write some code. Okay, so let's get started. As we had seen, a stack is a list or collection with this restriction, with this constraint, that insertion and deletion, that we call push and pop operations in a stack, must be performed one element at a time and only from one end, that we call the top of stack. So if you see, if we can add only this one extra property, only this one extra constraint to any implementation of a list, that insertion and deletion must be performed only from one end, then we can get a stack. There are two popular ways of creating lists. We have talked about them a lot in our previous lessons. We can use any of them to create a stack. We can implement stacks using A, arrays, and B, linked lists. Both these implementations are pretty intuitive. Let's first discuss array-based implementation. Let's say I want to create a stack of integers. So what I can do is I can first create an array of integers. I'm creating an array of 10 integers here. I'm naming this array A. Now I'm going to use this array to store a stack. What I'm going to say is that at any point, some part of this array, starting index 0 till an index marked as top, will be my stack. We can create a variable named top to store the index of top of stack. For an empty stack, top is set as -1. Right now in this figure, top is pointing to an imaginary -1 index in the array. An insertion or push operation will be something like this. I will write a function named push that will take an integer x as argument. In push function, we will first increment top, and then we can fill in integer x at top index. Here we are assuming that A and top will be accessible to push function even when they are not passed as arguments. In C, we can declare them as global variables, or in an object-oriented implementation, all these entities can be members of a class. I'm only writing pseudocode to explain the implementation logic. Okay, so for this example array that I'm showing here right now, top is set as -1, so my stack is empty. Let's insert something onto the stack. I will have to make call to push function. Let's say I want to insert number 2 onto the stack. In a call to push, first top will be incremented, and then the integer passed as argument will be written at top index. So 2 will be written at index 0. Let's push one more number. Let's say I want to push number 10 this time. Once again, top will be incremented. 10 will now go at index 1. With each push, the stack will expand towards higher indices in the array. To pop an element from the stack, I'm writing a function here for pop operation. All I need to do is decrement top by 1. With a call to pop, let's say I'm making a call to pop function here, top will simply be decremented. Whatever cells are in yellow in this figure are part of my stack. We do not need to reset this value before popping. If a cell is not part of stack anymore, we do not care what garbage lies there. Next time when we will push, we will modify it anyway. So let's say after this pop operation, I want to perform a push. I want to insert number 7 onto the stack. So top once again will be incremented, and value at index 2 will be overwritten. The new value will be 7. These two functions, push and pop, that I have written here, will take constant time. We have simple operations in these two functions, and execution time will not depend upon size of stack. While defining stack ADT, we had said that all the operations must take constant time, or in other words, their time complexity should be big O of 1. In our implementation here, both push and pop operations are big O of 1. One important thing here, we can push onto the stack only till array is not exhausted, only till some space is left in the array. We can have a situation where stack would consume the whole array, so top will be equal to highest index in the array. A further push will not be possible because it will result in an overflow. This is one limitation with array-based implementation. To avoid an overflow, we can always create a large enough array. For that, we will have to be reasonably sure that stack will not grow beyond a certain limit. In most practical cases, large enough array works, but irrespective of that, we must handle overflow in our implementation. There are a couple of things that we can do in case of an overflow. Push function can check whether array is exhausted or not, and it can throw an error in case of an overflow. So push operation will not succeed. This will not be a really good behavior. We can do another thing. We can use the concept of dynamic array. We have talked about dynamic array in initial lessons in this series. What we can do is, in case of an overflow, we can create a new larger array. We can copy the content of stack from older filled up array into new array. If possible, we can delete the smaller array. The cost of copy will be big O of n, or in simple words, time taken to copy elements from smaller array to larger array will be proportional to number of elements in stack or the size of the smaller array, because anyway stack will occupy the whole array. There must be some strategy to decide the size of larger array. Optimal strategy is that we should create an array twice the size of smaller array. There can be two scenarios in a push operation. In a normal push, we will take constant time. In case of an overflow, we will first create a larger array twice the size of smaller array, copy all elements in time proportional to size of the smaller array, and then we will take constant time to insert the new element. The time complexity of push with this strategy will be big O of 1 in best case and big O of n in worst case. In case of an overflow, time complexity will be big O of n, but we will still be big O of 1 in average case. If we will calculate the time taken for n pushes, then it will be proportional to n. Remember, n is the number of elements in stack. Big O of n is basically saying that time taken will be very close to some constant times n. In simple words, time taken will be proportional to n. If we are taking c into n time for n pushes, to find out average, we will divide by n. Average time taken for each push will be a constant, hence big O of 1 in average case. I will not go into all the mathematics of why it's big O of n for n pushes. To know about it, you can check the description of this video for some resources. Okay, so this pretty much is core of our implementation. We had talked about two more operations in definition of stack ADT. Top operation simply returns the element at top of stack. So top function will look something like this. We will simply return the element at top index. To verify whether stack is empty or not, this is another operation that we had defined. We can simply check the value of top. If it is equal to -1, we can say the stack is empty. We can return true, else we can return false. Sometimes pop and top operations are combined together. In that case, pop will not just remove an element from top of stack, it will also return that element. Language libraries in a lot of programming languages give us implementation of stack. Signature of functions in these implementations can vary slightly. Okay, now I will quickly show you a basic implementation of stack in C. In my C code here, I'm going to write a simple array-based implementation to create a stack of integers. The first thing that I'm going to do is I'm going to create an array of integers as global variable, and the size of this array is max size, where max size is defined by this macro as 101. I will declare another global variable named top and set it as -1 initially. Remember, top equal -1 means an empty stack. When a variable is not declared inside any function, it's a global variable. It can be accessed anywhere. so you do not have to pass it as argument to functions. And now I will write all the operations. This is my push function. I'm first incrementing top and then setting the value at top as x. X is the integer to be inserted, passed as argument. Instead of writing these two statements, I can write one statement like this and I will be good. I'm using pre-increment operator, so increment will happen before assignment. I also want to handle overflow. We will have an overflow when top index will be equal to max size minus 1, highest index available in the array. In case of an overflow, I simply want to print an error message, something like this, and return. So in this implementation, I'm not using a dynamic array. In case of overflow, push will not succeed. Okay, now this is my pop function. I'm simply decrementing top. Here also we must handle one error condition. If stack is already empty, we cannot pop. So I'm writing these statements here. If top is equal to -1, we cannot pop. I will print this error message that there is no element to pop and simply return. Now let's write top operation. Top operation will simply return the integer at top index. So now my basic operations are all written here. I have already written push, pop, and top. In main function, I will make some calls to push and pop. And I want to write one more function named print, and this is something that I'm going to write only to verify that push and pop are happening properly. I will simply print all the elements in the stack. In my main function, after each push or pop operation, I will make a call to print. I'm writing multiple function calls, two function calls on same line here because I'm short of space. Remember, print function is not a typical operation available with stack. I'm writing it only to test my implementation. So this pretty much is my code. Let's now run this program and see what happens. This is what I'm getting as output. We are pushing three integers, 2, 5, and 10, and then we are performing a pop. So 10 gets removed from the stack, and then we are pushing 12. So this is a basic implementation of stack in C. This is not an ideal implementation. An ideal implementation should be something like, we should have a data type called stack, and we should be able to create instances of it. We can easily do it in an object-oriented implementation. We can do it in C also using structures. Check the description of this video for link to source code of this implementation as well as of an object-oriented implementation. In our next lesson, we will discuss linked list implementation of stack. This is it for this lesson. Thanks for watching.